Welcome to another video. Now, in this video, what we will be focusing on is covalent bonding. All right, so if you remember, you learned covalent bonding firstly in grade 10, and then now we are dealing with it again in grade 11. So where it all comes from, before we even start and go deeper into covalent bonds, right, we must first understand a chemical bond in general, because a covalent bond is a type of a chemical bond, also known as an interatomic bond or interatomic force. Right, so how it works is, like I said, first we must understand a chemical bond. Right, so let's start here. Chemical bond. So imagine I have two atoms, right? So let's start with my atom 1. My atom 1 has a nucleus, which is what I just drew now. So a nucleus is usually positively charged. The reason for that is because in a nucleus, there is, or you will find protons and you'll also find neutrons, right? So neutrons carry a net charge of 0. And then the protons will be positively charged. So if you take the net charge of a nucleus, you will find that it's positive. It's a net charge of positive, right? So that's why it's positive. Now, that's our nucleus, and then now this is our electron cloud, or the outside shell of the atom, right, where the electron cloud will be. All right, so imagine this, that's our atom. Let's call it atom 1, right? Now let's say there's another atom here, atom 2. Let's put them close to one another. Okay, this is atom 2. Now what happens is, remember, center is our nucleus, and then around the nucleus it is surrounded by a cloud of electrons. Okay, a cloud of electrons, same as atom 2, there's a cloud of electrons. So every atom has a nucleus in the center, and then around that nucleus you will find a cloud of electrons. Right, so what happens is, when these two atoms want to achieve what we call a stable state, right, or when we put them next to one another, let's start there, what tends to happen is there will be forces of both attraction and repulsion between the two atoms, right? So how does that work? Let's focus on the nucleus first. So between these two nucleus, if you remember, we have a rule that says like charges repel and unlike charges attract. So if you check the nucleus or the nuclei of both atoms 1 and 2, you will find that they are both positively charged. So if these two atoms are next to one another, these two nuclei, they will do is they will repel each other. So there will be a force of repulsion on atom 1 due to the nucleus of atom 2. Let's draw that force of repulsion vector like that, right? So this is the force of repulsion on atom 1 due to atom 2. So the nucleus of atom 1 due to the nucleus of atom 2. Okay, but remember, they are both exerting this force of repulsion on one another. So nucleus of atom 2 will also feel a force of repulsion due to the nucleus of atom 1. Right, so that's what will happen. Now, another thing that will happen, okay, we can label these forces. I can call this the force of repulsion. Okay, this is the force of repulsion on nucleus 1 due to nucleus 2. And then what will happen is, on the other hand, on atom 2 will also feel a force of repulsion due to the nucleus of atom 1. Okay, so we'll just say force of repulsion on nucleus 2 which is the nucleus of atom 2, due to the nucleus of atom 1. All right, so that's what will happen. Now, another thing that will happen is the electron cloud that surrounds atom 1 will be attracted to, let's just focus on one electron. Let's say we are looking at this electron, right? So the electron cloud that surrounds, let's use a different color. The electron cloud that surrounds atom 1 will be attracted to this nucleus of atom 2. So there'll be a force of attraction there, like this. Okay. Why? Because these two are unlike charges. The electron cloud that's surrounding atom 1 is negatively charged, and then the nucleus of atom 2 is positively charged. Okay. The same will happen with now the electron cloud surrounding atom 2, right? It will be attracted to the nucleus of atom 1. So there will be another force of attraction there, like that. Now, if we take a net force of these forces that are interacting between these two atoms, because if you check carefully, you will notice that we have seen two forces here. There are repulsive forces, which is when nucleus of atom 1 is exerting a force of repulsion on nucleus of atom 2, or or vice versa, right? Because it's an action-reaction pair. And then there are now forces of attraction, which is what the nucleus and the electron clouds exert on one another, right? If we sum those forces and we find the net force, if that net force is net attractive, then these two atoms will form what we call a chemical bond. But if that net is repulsive, then these two atoms will not form a chemical bond. So now that's how a chemical bond is formed. Okay, so here we have, right, so I'm labeling this. We have force of attraction by electron clouds on nuclei, right? So that's what happens. Electron clouds are for both atom. Nuclei is just a plural for nucleus. All right, so that's what happens. So now a chemical bond then by definition becomes that's a mutual attraction between two atoms, which is resulting from this simultaneous attraction between their nuclei and their outer atoms. All right, so that's how we typically define a chemical bond. It's just that mutual attraction between two atoms as a result of this simultaneous attraction between their nuclei and their outer electrons, or this electron cloud. All right, or let's just call them outer electrons so that you guys get it. Right, because even if you check the diagram, you can see that they are outside the nucleus. Right, so now we can define our chemical bond. But remember, we said it forms, let me just note it here. A chemical bond will form if the net force is attraction between atom 1 and atom 2. So remember, atom 1 can be any atom. For instance, we can say, e.g., it can be hydrogen, and then this one can also be hydrogen, or it can be anything. It can be chlorine, and so on and so forth, right? So they can be atoms of the same element or atoms of different elements, okay? So it doesn't matter. But for the sake of this example, we just call them atom 1 and atom 2. Okay, so now we define what a chemical bond is. So a chemical bond is a mutual attraction between two atoms resulting from the simultaneous attraction between their nuclei and the outer electrons, right? As already I've stated, I think for the third time now. So now let's write it here. All right, So remember, we also said that a chemical bond is also known as the interatomic force or interatomic bond, right? So there's a reason for that, because it exists between two atoms, hence the word interatomic. Remember, inter means between two things, right? And then that's why a chemical bond is also called interatomic. Or forces, right? So that's one thing we need to note. Now there are three types of these interatomic forces or these chemical bonds that we normally look at, right? So we have 1, an ionic bond, 2, a covalent bond, which is the main focus of today, and then 3, a metallic bond, right? So they differ depending on which atoms or which elements are involved or participating in that specific bond. All right, so how it works, let's state this here. All right, so these are the types that we have of our interatomic forces or chemical bonds. All right, so these words are used interchangeably. They mean pretty much the same thing. Now, what happens is with ionic bonds, right, how they're different or how each of these bonds are different from one another, it depends on the types of elements or atoms that are involved in that specific bond, okay? So for ionic bonds, what happens is we have between nonmetal and a metal, right? So they occur between a non-metal atom and a metal atom. For instance, they can occur between sodium and chlorine, okay? A non-metal and a metal, where of course the sodium is the metal and the chlorine is the non-metal. All right, so we can put it here and say in fact, let's just put it here. Example, we can have sodium plus chlorine. All right, so e.g. sodium, no, chlorine, because this is a non-metal, plus our sodium, which is a metal. Okay, so that's what happens when we talk about ionic bonds. And then covalent bonds, which is our focus for today, will typically be between nonmetals. All right, so nonmetal plus nonmetal atoms. And then a metallic bond. So with metallic bonds, these ones, they occur only between metals. Metal plus metal atoms. So now, our main focus though is on covalent bonds for today. This is our main focus. All right. So now let us get into more detail when it comes to covalent bonds. Firstly, there are things that we must understand when we talk about covalent bonds, and that is the number of valence electrons and how it relates to the group number of the specific atom or element. So remember, we were talking about metals and non-metals when we were talking about the types of the interatomic forces or interatomic bonds. All right, so remember how we do it is if you check your textbook, if we have a line here, we usually draw a line here in like stairs, like a staircase. We come here, we divide like this, right? And everything to the right of this line is what we would call our non-metals. And then everything to the left is what we would call our metals. All of it except hydrogen. Okay, so hydrogen is not a metal, it's a non-metal. So remember that. So everything this side, we would call them our non-metals. Right, and then everything going that side is where our metals are. Except, okay, this is big. Except hydrogen. Okay, we don't include hydrogen. So that's what I'm talking about. So now, and then what happens is all of these have a valence. So valence electrons. So those are the electrons in the outermost shell of an atom, right? So these are actually the electrons that will participate in our covalent bond. Why are they participating in the covalent bond? It all comes to what we call an octet rule, right? So, all right, so we've said quite a lot of things there. I've mentioned valence electrons, I've mentioned octet rule. Let's bring it back to, okay, first off, we must make it clear we're now entering strictly talking about covalent bonds. Which is the main topic of this video, right? By definition, covalent bond is where two atoms meet and then they share a pair or more of electrons, right? To satisfy or to fill their valence shells. Right, so now what that looks like is, first things first, we have to understand what do we mean by valence electrons, or what do we mean by valence shell. Right, so when we say valence, we are basically saying valence shell, or let's just say valence electrons, okay? So you were just saying outer electrons in the outermost shell of the atom. Right, because remember, an atom will have multiple orbitals, right? So these valence electrons are the ones that are in the outermost shell of that atom, okay? So it's in the s orbital. Now what happens is these are the same electrons that will participate when we form a covalent bond, all right? They will participate they participate in the formation of the covalent bond. Okay, that's another thing we need to note. But of course, there's a bit of caveat to this. Not all of them will participate, but generally, the valence electrons are the ones that participate in the formation of a covalent bond, right? But later on, we'll speak about the ones that don't participate, which are usually in pairs. They are called the lone pairs, right? So those ones don't necessarily participate, but for now, keep this in mind that valence electrons are responsible for participating during the formation of covalent bonds. So now let us remind ourselves of what do we mean by valence electrons. So like we said, valence electrons, they are in the outermost shell of an atom, right? So how we find them, we come to the periodic table. If you check this I, double I, and so on, these Roman numerals, this one stands for 1, this one stands for 2, that for 3, 4, 5, 6, 7 until 8. Okay, those Roman numerals, that's what they stand for, 7 and 8. Right, so which is the same thing that we've listed here. We have the group number 1. The number of valence electrons are 1, which is represented by this Roman numeral 1. So what this means is if I go to this column 1, or this column, this group, for group 1, every atom or element in this group will have a valency or a valence electron of 1, which means in its outermost shell or in its outermost orbital, it has 1 electron there. Okay, that's one thing we need to note. If I come to this group where there's beryllium, magnesium, calcium, and so on, these ones have a valence of 2 or 2 valence electrons, which means in their outermost shell there are 2 electrons, just 2. All right, and then we skip this middle row, we skip all of this, right? These are called transition metals. We skip all of them. The reason for that is because they don't have a strict valency, right? So if you check for what we've been doing so far, group 2, we know that all these atoms here or all these elements will have a valence of 2, or in the outermost shell they will only have 2 electrons. Well, with transition metals, that rule does not apply, because you might find that this one, scronium, and that element, they won't have the same valency, right? So it adds a bit of complexity in a sense, right? So we can't really give them a rule and say, okay, all atoms in this group will have 4 valence electrons. Okay, it doesn't work like that. With them, it's different. Also, the valency of these transition metals differs depending on the type of reaction they are in. All right, so we don't have a specific rule for them. That's why we skip them, because they don't behave in a consistent manner. So we focus on these ones, group 1, 2, and then we jump all of these ones and we start from 13, 14 until group 18 again, right? Because those ones follow a strict consistent pattern that we can group. Okay, so now when we go to group 13, again we have 3 valence electrons and so on until group 18. So with group 18 we have 8 valence electrons. So why is this important? Right, so now these valence electrons, what they do now is, the reason we worry about them is because of what we call the octet rule, right? So the octet rule says for an atom to be stable, it needs to have 8 electrons in its outermost shell, with the exception of hydrogen or those group 1 metals there, right? So when I say exception, it means it doesn't include hydrogen. Okay, so the octet rule says, remember, oct just means 8. Oct, which is a prefix, it means 8. Okay, so when we say octet rule, think of it as a rule of 8, right? So these atoms need 8 electrons to fill their outer shell, right? Except hydrogen. It only needs one. Right? Another exception, of course, is the halogens, which are in group 18, but we'll get to that. So with hydrogen, it only needs one to fill its outer shell. Why are they filling their outer shell? Electrons needed. Of course, this is not a formula per se, but just as a rule, to fill valence shell would be 8 minus the number of electrons in that valence shell. So we call them valence electrons. Right. So it's 8 minus the valence electrons. So if we go to group 2, for instance, right, where in group 2 we have a valence electron or a valence number of 2, which means there are 2 valence electrons there, then how many do we need? We would say 8 minus 2. That means every atom in group 2 will need exactly 6 electrons for them to fill their outer shell. Same as if we went to group 13. Group 13 has 3 valence electrons. So I would say 8 minus 3. That means every atom that is in group 13 needs exactly 5 electrons for it to fill their valence shell. Right, that means now whichever other atom that it finds, right, it will try to make sure that it benefits about 5 electrons from that atom. Right, so in the case of covalent bonds, the way it works is usually these 2 atoms will come together and they will check, okay, in my case I have, let's say, 5 valence electrons. I need 3 valence electrons for me to have 8 electrons and they will be stable. Okay, so let's fix this so that they are stable, not stability. All right, so that's how it normally works. Okay, so let me remove that. So we have a visual way of seeing how these atoms behave when they meet one another in order to form a covalent bond. So a covalent bond is essentially now when these 2 atoms are meeting and they decide to share their electrons, because they benefit from sharing these electrons, and the main benefit of that is that they get to fill their outer shell and thereby becoming stable. Of course, when they now fill their outer shell by sharing these electrons, what ends up happening there is they form a new molecule. Okay, so we will get to see how that happens using what we call a Lewis dot diagram. All right, so I think we forgot to add our definition for covalent bond there. Let's just do this. Let's add our definition for covalent bond. We say a covalent bond is essentially a sharing between two atoms where they share electrons in order to form a molecule. All right, let's write it. All right, so a sharing of electrons between atoms. Remember, it could be just between two atoms or more in order to form a molecule. All right, that's what we mean by covalent bond. Now, again, what happens is these atoms will have valence electrons, and depending on how many valence electrons they have, they will then need a certain number of electrons to fill their outer shell, right? And then they will want to share electrons amongst each other so that each of them gets to fill their outer shells. So what we normally do is we use Lewis dot diagrams to then visualize how they share these electrons. Okay, all right, so that's what we pretty much are talking about when we're talking about covalent bonds. Right, so let us check how we normally use these Lewis dot diagrams to visualize how atoms share electrons between one another in order to reach a stable state. Right, remember what we said here. The reason these atoms are trying to fill their outer electron shells is because they want to achieve a stable state. So they are stable. All right, so they are more stable when their outer shell is filled than when their outer shell has electrons that are missing. So when the outer shell is filled to 8, then they are more stable. When the outer shell still has less electrons, less than 8, then they are not so stable. Right, so what this means, if we come back to our periodic table, is every group until 8, because this is what, 3, 4, 5, 6, 7, every group until group 18, right? Every atom from every group until group 18, before group 18, is unstable and therefore will participate in covalent bonding with other nonmetals in order to reach stability, right? Because remember, covalent bonding only occurs between nonmetals, except the ones in group 18. The reason for that is if you check the valency for group 18, it is 8. So they have already filled their outer shell, so they do not need to participate in covalent bonding, all right? Because they don't have any space to fill more electrons. They have already reached 8. All right, so let's check how we use Lewis dot diagrams to visualize how these atoms bond, or how they form a covalent bond. All right, so let's start with, for instance, F2, right, which is fluorine, right, the fluorine gas. Now, fluorine gas, if we go and check in our periodic table, because if you check here, it means we have 2 fluorine atoms that bonded to form this fluorine gas, right? So we want to see how we got to F2. So these will be our examples. Right? We're starting with fluorine gas. So let's go and check on our periodic table. Fluorine gas is in group 17, right? Since it's in group 17, it has 7 valence electrons. Remember, the octet rule says says that we need 8 valence electrons. So what does this tell us about fluorine? It means fluorine will need 1 more electron in order to fill its valence shell, because it has 7 already, so it needs 1 more. All right. Okay. Fluorine is in group 17. It has 7 valence electrons, and it needs one electron to fill its valence shell. So let's check how fluorine would bond with another fluorine atom in order to form F2, thereby filling its valence shell. So how we do it is we have fluorine, right? And now we want to represent the valence electrons in fluorine. What we do is we usually use dots or crosses, right? So that we can tell these atoms apart when we draw these Lewis dot diagrams. So let's start with dots. So what we do is we know that fluorine has 7 valence electrons. So we will list them. We will add them on next to around the fluorine atom. So 1, 2, 3, 4. Right, so now we've filled all 4 sides, and then we start from the first one again until we reach 7, of course. 5, 6, and 7. Now notice one thing. So we have ones that are in pairs, which are 1, 2, 3, and there's only 1 electron that is not a pair, right? That 1 electron is the one that will be shared with the other fluorine atom in order to fill this valence shell, right? Because the other one are already in pairs, so they are fine. They won't participate in this covalent bonding reaction that's happening here, right? This is the exception I was talking about when I said valence electrons participate in the formation of a covalent bond, but there's an exception. These ones that are already paired, they will not participate in this covalent bonding. So we call them lone pairs, right? These are called lone pairs. All of these. I'll just label one, but all of them, the ones that I've highlighted, are called lone pairs. Okay, so L-O-N-E, lone pairs. Now it means the other fluorine atom will be the same, but now so that we can tell them apart, we will use crosses for this one. So again we start 1, 2, 3, 4. We start from 1 again, 5, 6, and 7, leaving only this one as the one that will be sharing so that fluorine fills its outer shell. So currently fluorine has 7 atoms in its valence shell. So now what about when it shares? So what will happen is, if you check, the math says if these two come together and they share these two atoms, these 2 electrons that are just not paired with any other electron, what they will do, they will create a new pair, and that new pair, because they'll be sharing it, both of them, it will allow them to fill their outer shell. So let's look at it when now they are sharing this outer, these electrons. So we can rearrange these to fit our purpose. So what we can do, I will put the pairs like this now, the lone pairs, and then I will put the single electron here so that I can draw this structure properly. Then these two will combine. This will combine with that, right? They will combine. These two. So, such that they will create a pair that will be shared between these two fluorine atoms. This is the other fluorine atom, right? I haven't changed anything. So what happens now, if we check the first fluorine atom, if we count the electrons that are in its valence shell, you will find that now it's 1, 2, 3, 4, 5, 6, 7, 8. So it is now stable. So since the middle pair is the one that's being shared, we can also do the same for the other one. If we count the electrons that are now in its outer shell, it's 1, 2, 3, 4, 5, 6, 7, 8. So now it is also stable. Okay? So that's what happens in covalent bonding. They were just sharing this pair of electrons so that they reach a stable state. So now they are stable. So you can remove that. Now they are stable. So if you notice, they have created a new pair. We will call this pair our bonding pair. It's the one that bonds them together. This pair is our bonding pair. Since there's only one bonding pair, remember pair means two things that go together, right? Whenever you wear your shoes, since you have 2 feet, they come as two. They come as a pair, right? Same thing as here. We have 2 electrons that are being shared amongst these 2 fluorine atoms, and we call them a pair of electrons, right? We call that pair a bonding pair. So since the bonding pair is only one, there's one bonding pair. If there were 2 bonding pairs, it means there would be 4 electrons, but there are 2 electrons, so there's one bonding pair. It will create a single bond that will be represented like this, using a line between fluorine and fluorine. So this will be a single bond. Okay, between fluorine and fluorine, because they only share one bonding pair. All right, so let's list lone pairs in our final fluorine gas atom. And then let's also check our bonding pairs. Right? Our lone pairs, we have 1, 2, 3, 4, 5, 6. So basically we have 3 lone pairs, but in total we have 6, which is 3 per fluorine atom. So we have 6. I'm talking about the final structure, this one, the final structure on the right hand side of the arrow. Okay, that means we have 3 per fluorine atom. Okay, and then how about the bonding pairs? Bonding pairs, there's only one in the middle, which is 1. So a bonding pair will always be in the middle of the 2 atoms. Okay, it won't be outside. So the other pairs that are outside and they are not in the middle of the atoms, just know that those are usually lone pairs. Let's do another example. That's our fluorine. Let's do another example. Let's say now we are looking at the hydrogen gas atom, or the hydrogen gas molecule, not atom. Right, so what happens here, if you check, remember with hydrogen, it's an exception. It's an exception because instead of needing 8 electrons to fill its outer shell, it actually needs just 1. All right, so hydrogen is in group 1 and it happens to need just 1 electron to fill its valence shell. Okay, so it needs just 1 electron to fill its valence shell. So let's check how it behaves. So you'd have an hydrogen atom meeting another hydrogen atom, right? You can put it here. No, this is not good. Let's put it there, then let's put it here. And then these two will share such that both of them get to have 2 electrons in their valence shell. So if you check hydrogen 1, if we look at hydrogen 1 only, it has 2 electrons in its outer shell. If we look at only hydrogen 2, it will also have 2 electrons in its outer shell. So for this covalent bonding of 2 hydrogen atoms to form the hydrogen gas molecule, what we notice is that there is a bonding pair, which is this one in the middle, but there are no lone pairs here. There are no lone pairs. This is our bonding pair. But lone pairs are nowhere to be found. All right, so since there's only one bonding pair, what will happen is the hydrogen gas molecule will have a single bond represented by just one line between these 2 hydrogen atoms. It will have a single bond between its hydrogen atoms. All right, that's it. And then if we want to count the number of lone pairs and bonding pairs, there is only 1 bonding pair and 0 lone pairs. Okay, unlike here where we had 3 lone pairs per fluorine atom, making it 6 in total. All right, so here we have no lone pairs, but only 1 bonding pair. All right, lone pairs 0, bonding pairs 1. Right, let's look at water as another example. H2O. With water, we have 2 elements now, 2 atoms that are involved. But unlike our previous 2 examples, water has 2 different atoms that are involved. It's oxygen and hydrogen. If we go to our periodic table, oxygen is in group 16 and it has 6 electrons in its valence shell, which means it needs 2 more in order to reach 8. And then hydrogen, on the other hand, will need just 1 more. All right, so there are 2 hydrogen atoms and 1 oxygen atom in the water molecule. All right. Okay, said water, hydrogen, group 1 only has 1 valence electron, and then it needs 1 more. Remember, oxygen, group 16, it has 6 valence electrons. It needs 2 more to fill its valence shell. Remember, octet rule, we need 8. The only exception is hydrogen. All right, so let's check how they behave. Now let's start with hydrogen. We already know we'll move a bit faster now. It'll just have 1 there. We'll use crosses for the hydrogens since they are both the same, and for now we'll use dots for oxygen. Remember what we said? Okay, this is our oxygen. Okay, so our oxygen atom will have 6 valence electrons. So let's start 1, 2, 3, 4. We go back again, 5, and since I'll be joining them from left and right, the hydrogen atoms, let me label 6 here, but the 6th one is supposed to be here, right? It doesn't really matter when you draw these things, as long as the lone pairs are the correct number and the single atoms are also the correct number. But even if I put my lone pairs like this, or I put them like that, or I put them like that, it doesn't matter really, okay? As long as it's the correct number of valence electrons and the lone pairs are the correct number as well. So I'm putting them here just for my convenience, right? So it has 6 valence electrons with 2 lone pairs, okay? So these are the pairs of electrons that won't really participate in my covalent bond. Of course, they need a special type of covalent bond to participate, but I will show you later on what that looks like. Okay? Now, if you check, these two are hanging. They don't have a pair, so that's why they will participate in this covalent bond. So this one will go and share with that one, and this other hydrogen electron will go and share with the other oxygen electron that's just without a pair, without a partner. Okay, so that's what it would look like. Let's draw it here. You will have, in fact, we can take this as is. Let's put it here. This will go there. Okay, let's do it properly. Okay, our first hydrogen there, and our second hydrogen there. Hydrogen now has 2 electrons. The other hydrogen as well has 2 electrons. Oxygen has 8 from 6. So everyone is now happy. Okay, so if you check, we have 1, 2 lone pairs, and then we have 1, 2 bonding pairs. So here we have 2, 2. All right, so what that means as well is, since there's only 1 bonding pair between each hydrogen oxygen bond, see, if you check between hydrogen 1 and the oxygen, there's only 1 bonding pair, and then between hydrogen 2 and that oxygen, there's also 1 bonding pair. It means there will be a single bond as well for this one. So you'll have O, oxygen in the center, and then it's bonded to hydrogen there and another hydrogen there. So there's a reason why it's this type of shape. It's because of the lone pairs. They are repelling the bonding pairs, but we will talk about that in another video where we use the VSEPR theory to find these shapes. Okay, for now, this is what it would look like. So there are single bonds between the OH atoms. All right, so let's check one more example, and then we will check a past paper problem. So let's check nitrogen, the nitrogen gas molecule. All right, so nitrogen, if we go to our periodic table, it's in group 15. And if it's in group 15, it needs, or it has a valence of 5. So in its outer shell, there are 5 electrons. So how many does it need to fill its outer shell according to the octet rule? It needs 8 minus that 5 that it already has. So that is 3. It needs 3 more. All right. Okay. So it needs 3 more electrons to fill its valence shell. So let's see how that looks like. So if we check N, because there are two atoms that combined in order to form that nitrogen gas molecule. So it has 5 valence electrons. So that's 1, 2, 3. Sorry, let's do it from scratch. 1, 2, 3, 4. We go back again. 5. Okay. So it only has 1 lone pair. So that means the same happens for the other nitrogen atom. We'll just copy that because it's the same atom. So you see now there are 3 electrons that are not lone pairs. So they are just single electrons around that valence shell or around that nitrogen atom. So now, because nitrogen needs 3 to fill its valence, how it forms that nitrogen gas molecule is all of them, they get paired. This one gets paired with that one. That one gets paired with that one. And lastly, this one gets paired with that one. So you'll have 3 bonding pairs here. So this means you'll have a triple bond. So let's draw it. The first nitrogen will be there. We'll have our lone pair here at the top, right? The other nitrogen will be there. You'll have our lone pair here at the top. First bonding pair, this nitrogen electron that was alone is paired with another nitrogen atom that was another nitrogen electron that was floating by itself there as well. Another one here is paired with another one there. Another one here. Remember, there were 3 of them. 1, 2, 3. That were single electrons. And there was only one lone pair. So, lone pair number 1, lone pair number 2. So here in the final nitrogen gas molecule, we basically have 2 lone pairs. But how many bonding pairs do we have? If you check, 3 atoms had to make a pair. 3 electrons had to make a pair. 1, 2, 3. From both sides of the nitrogen. Nitrogen 1 had to offer its 3 single electrons. Nitrogen 2 also had to offer its 3 single electrons, thereby forming 3 pairs of bonding pair between these 2 nitrogen atoms. So there's bonding pair number 1, bonding pair number 2, and bonding pair number 3. So what that means is we have 3 bonding pairs. So since we have 3 bonding pairs, remember, one bonding pair gives us 1 bond. Second bonding pair, another bond. Third bonding pair, another bond. So how this would look like if we draw our lines like we've been doing for the other ones, we would get that the nitrogen atoms are bonded by 3 bonds. So this is what you would call a triple bond. 1, 2, 3. That's what you would call a triple bond. So now it means once the nitrogen atoms have reached their stable state, you would find that they are bonded by 3 bonds, by a triple bond. All right, so in this, once we reach our product there, which was on the right hand side of our arrow, that is our stable state. Now at this state, nitrogen gas is very much stable. Okay, so it will have 2 lone pairs and 3 bonding pairs. Okay, so there's one last molecule as well where this happens, where you have 3 bonds We call this hydrogen cyanide. It's quite volatile, flammable as well. So let's check how this one would bond. Right, with hydrogen cyanide, remember hydrogen will have one valence electron. Then you have carbon. Carbon is in group what? Carbon is in group 14. It has 4 valence electrons. So if we go back, it will have 1, 2, 3, and then 4. Then you have nitrogen. We have already established nitrogen has 5. So let's put crosses because I don't think we can use anything else. Okay, so how would this work? All right. You would find that H would take one of these single electrons that are surrounding carbon. So you'll have H and carbon forming one bond there. Now you're left with 3 more. And these 3 more that are remaining, they will then form pairs with the 3 electrons, single electrons around the nitrogen atom. All right, so you'll have 1 forming with 1 nitrogen electron, another one, another nitrogen electron, another one, and then you have your nitrogen there as well. So that's what happens. And then if you check here, there are 0 lone pairs, but there are about 1, 2, 3, and 4 bonding pairs. Okay, those are our bonding pairs. And then remember, the number of bonding pairs will tell us whether that's a single, double, or a triple bond. So between H and C, there's only 1 bonding pair, which means we will get a single bond. But between C and N, or between carbon and nitrogen, there are 3 bonding pairs. 1, 2, and 3. Then there's N. So we'll get a triple bond there. Okay, so that's what will happen in this case. All right, so that's what will happen. So now you might be wondering why we drew them like this, because if you check on between H and C, the bonding pair is like X and then the dots, and we've been doing them like that. But it becomes tedious if we want to draw 3 of them and we arrange them in this fashion. So because now you would have something like this, and then you would have C and N. That looks very tedious. So that's why we change the arrangement such that they can fit this space. They take less space, and then we just do that, and we get 3 bonding pairs. Okay, so we don't do that long chain I showed you first because it's tedious and it looks weird and it fills up a lot of space. All right, so that is it for these examples. Perhaps as your own homework, you can try this one. Try HOCl, right? So the atoms that are involved here, you have hydrogen, oxygen, and chlorine. Try that molecule and try drawing a Lewis dot diagram for that. Take out the number of lone pairs, the number of bonding pairs, and then take out whether or not there's single or double or triple bonds between these atoms that make up this molecule. All right, so that's your homework. And then for the sake of completing our definitions, let's write our definition for bonding pair and lone pair. So a bonding pair, we said, is just a pair of electrons that is shared between 2 atoms in a covalent bond, right? And then a lone pair, it's a pair of electrons as well, but it's found in the valence shell of an atom, and it's not shared during the covalent bonding. Right, so a pair of electrons in the valence shell of an atom that is not shared with another atom. Right, so that's it. I think I've given you, or we've seen enough examples of bonding pair, lone pair, that you have a visual evidence of what those look like, right? So let's go on and check a past paper problem or activity. All right, so this is from a June 2025 Mpumalanga paper. Right, so that's question 2, and we are told that two fluorine atoms, they combine by a chemical bond to form a fluorine molecule, okay, as shown in the equation below. All right, now we are told to define, or we are asked to define, the term chemical bond. Remember, we said a chemical bond, it's just a mutual attraction between two atoms as a result of the result of the simultaneous attraction forces, their outer electrons and their nuclei. Right, we wrote that definition, I think. Yes, so we'll just take that. So remember, these definitions, you have to make sure that you know them beforehand, so that whenever you go to a test or an exam, you can get these free marks, okay? Don't leave them out. Don't be lazy to memorize these definitions. They are free marks. Free. Okay. So 2.2. How does the stability of the combined atoms, which is the F2 gas, compared to that of the individual atoms? Choose from lower, higher, or equal to. Write down a reason for the answer. So remember, if these atoms, they exist without combining, right? So for instance, fluorine by itself, we said it has about 5 valence electrons? Was it fluorine? Oh, it has about 7, right? It has 7 valence electrons, and because of that, it is not stable. But once now it combines with another fluorine gas atom to form the new fluorine gas molecule, what happens is they each get to fill their outside shell from having just 7 to having 8 electrons in their outer shell, and thereby reaching a stable state, right? So they are more stable when they are together than when they are individual atoms. Okay, so we can say higher. Is it, how does, yes, it's higher when they are together than when they are individual atoms. Now we're asked to write a reason for this answer, right? And we said that, again, when they are together, they are able to fill their outer shell than when they are individual atoms. Right, so the combined atoms will have an octet structure in their valence shell, while the individual F atoms will only have 7 valence electrons, and we know that it's not stable. Right, so another explanation for this is that when these two atoms are forming a bond, they release a certain amount of energy we call the potential energy. We explained this in another video. You can go watch it. So as they bond, they form this single bond, right, that will form here, or whatever bond order that they will form. But in the formation of that covalent bond, they release a certain amount of potential energy until they reach the lowest possible potential energy, and that at that point they will have reached stability, right? So the lower the potential energy in the system, which is the F2 molecule, the higher the stability, while when they were individual atoms, they had a higher potential energy, so they were more unstable. So as we lower that potential energy due to bond formation between these two atoms, therefore we also get to have a higher stability. But as we increase, we get to have a lower stability. So that's why. So you can also explain it using that logic, right? So I've already written it here. The fluorine gas molecule will have a lower potential energy than individual F atoms, making it more stable. All right. Now consider the F2 molecule. Draw a Lewis dot diagram of F2. We've already done this one. And write down the number of lone pairs of electrons in the molecule. I think we said that was 6. Let's go check. So yes, we can draw it. We can just take this. So since we were not asked for the whole reaction, we can just draw the Lewis dot diagram. But to be safe, you are welcome to draw the whole thing. So we can just bring that here. That's 2.3.1. You won't be penalized for drawing the whole thing. You don't have to highlight these ones. Alright, so this is how the Lewis dot diagram will look like, okay? Now we are asked for the number of lone pairs in the molecule. So if you check, the molecule has, remember we counted them, it has 1, 2, 3, 4, 5. It has 6 lone pairs, okay? 1, 2, 3, 4, 5, 6. Then the 7th pair is the bonding pair, so we can't count that one. So our answer to 2.3.2 is 6 lone pairs. All right, now 2.4. Let's write our 2.4. All right, so ammonium ion NH4 plus is formed by the reaction of ammonia NH3 with hydrogen ion according to the following equation. Okay, we see the equation. Draw the Lewis dot diagrams to show how NH4 plus is formed. All right, so this is the last part about the covalent bond. All right, so it's the one I told you about, that sometimes it doesn't always happen that we need an atom participating in the bond to have at least an electron that it can share with the other atom. Sometimes it comes and it just doesn't have anything to share, but the atom that it's going to share with already has all the electrons. So what that would look like is exactly what they are asking us here. So this is an example of dative covalent bonding. This is what you would call dative. So the best way to illustrate this one is through an example. Hence, I left it for this past paper problem. Bonding. All right, so how does it look like? So here, you have NH3, and then it's going to bond with that hydrogen ion to form NH4 plus. Right, so NH3 already, it looks like this. If we draw NH3, remember N has one lone pair. If you remember from our example, let's just go back quickly. N has about 5 valence electrons with one lone pair, and H obviously has 1. So let's draw N, right? So NH3 will have, okay, that's another one. It has 3 hydrogen hydrogen atoms, right? So in its Lewis dot structure, hydrogen will bring 1 electron there, another electron there by hydrogen, and another electron there by hydrogen, forming about 3 bonding pairs. Okay, so as it forms these 3 bonding pairs, if you check, it's done sharing. So now it's only left with that lone pair. Okay, so it means it cannot at this point participate in a normal covalent bonding. So that's why it can only do dative covalent bonding from here onwards. So when we come and add this H plus ion, right, let's now focus on this H plus ion. Remember, this is an H plus, it's an ion. This and that are not the same thing. This one is just an atom, a normal element. This one is an ion. So do you remember the difference? The difference is, if you see a plus here, they just omitted the 1. There was supposed to be 1 plus, but they don't write the number unless it's greater than 1. So maybe if it was 2, they would write 2. But if it's 1, they just write the plus. We just write a plus. We don't write the number. What this means is, this hydrogen, what happened to it is it lost 1 electron. So now it has extra protons. It has at least 1 extra proton than the number of electrons. So what does it mean for our valence structure? In our valence structure, it means now it doesn't have this X. It's completely empty, if you can think about it. So it needs exactly 2 electrons to fill its valence structure, right? So in normal circumstances, you would have H, and H would need 1 electron to fill its valence structure or its valence shell, right? So it would need only 1. But that's when it's not an ion. That's just a hydrogen atom, a normal hydrogen atom. But now once it's an ion, it means that 1 has been removed. So now it has 0. So it needs 2 to make that 2. But when it had 1, it only needed another one so that it can get 2. But now that it has 0, it means it needs exactly 2 electrons to form a proper valence structure. So what that would look like is, the 2 that it needs is fortunately exactly that lone pair. So this hydrogen will go, this whole hydrogen, this entire hydrogen ion will go here, and it will get that exact 2 number of electrons that it needs. So let's draw our new structure and how it would look like. First things first, we draw brackets. you don't leave these brackets because this now is a dative covalent bond, right? Okay. And then we take our ammonia, we bring it here, and then our hydrogen atom will come and sit on top of these two. Now this is our new ammonium ion. So after the brackets, what we do, we put a plus sign to show that the ammonia this ammonia has gained an extra proton. So now it has more proton than it does electrons. All right, so that's what we normally do. All right, that's what we normally do. So this plus sign, you never leave it out. First square brackets, then the plus sign. You never leave those two out. All right, so that's what typically happens in dative covalent bonding. Here's another example, right? So what happens if now, okay, before we go to that example, so let me just do, if you check, we had NH3, right? And it bonded to its H plus to form NH4 plus. That same plus that you see here is the same plus that you see here outside this bracket. You never leave it out, okay? So now let's check this other example. Water is also another example. If you have water, right, and then you add hydrogen and hydrogen ion, not just hydrogen, a hydrogen ion, what you tend to get is hydronium ion, which is H3O plus. It's an example of a dative covalent bond as well. So how this works is you take the structure of water, which you would have the oxygen there. And remember, oxygen also has two lone pairs in its valence electrons, right? Two lone pairs, and then it has those other single electrons that were able to bond with the hydrogen to the other two hydrogen atoms. Okay, now this hydronium ion comes, it needs exactly 2 electrons, right? So it'll just, this whole hydronium ion will go there, right? So it'll go and sit there or at the bottom, it doesn't matter, because there are 2 lone pairs. It'll choose one of those lone pairs, right? And then what we end up having is a new ion called hydronium ion. We have this water, right? We have our water there, and then our hydrogen there, our extra hydrogen now, and then we put the plus outside the brackets. Okay, so that's what happens here. So this is in essence what dative covalent bonding would look like. Okay. All right, so this concludes our lesson and video for today. I'll see you on the next video.